the contributions that we've made to offshore HVDC Grid Technology Qualification. Then you'll get some key messages from each of the relevant work packages with a final TRL impact assessment from the promotion project. And at the end of each of the sessions, we'll do a direct Q&A before concluding. So overview contributions. If you look at today's HVDC schemes, it's point-to-point connections, but to realise the offshore wind capacity, we'll need to move to something more like the grid that you can see in the middle of the screen. And within promotion, if you zoom in to the bus, and some of the things we'll be covering today is there's the DC protection system that goes around that with the associated Ieds. You have the breakers that are a fundamental part of it, and you also have the introduction of HVDC GIS, so you can compact it down and make it something that you might be a bit easier to fit into a platform offshore. And on top of that as well, we've got the overall HVDC system controls and the offshore wind farm controls. So within this breakout session, you'll hear from myself about work package 9, which looked at the HVDC grid protection system demonstration. You'll hear from Renee about the circuit breaker technology verification. You'll hear from Yui about the GIS tests and demonstrations, and you'll hear from Philip about the DC grid and offshore wind control demonstrations, before finally we hear from Rian about the TRL impact assessment that promotions had on getting ready for this meshed offshore DC grid. So as we go, it's split into those work packages, so you'll get a brief introduction from each of those work package leaders as we go, and then we'll have a good 10-15 minutes for Q&A as we go. I'd invite you to keep asking questions starting now, and we'll capture them and come to them at the relevant Q&A section. You can write your questions in the chat and we'll pick them up as we get into the sessions. If you've got any questions after it, all our contact details I think are embedded in these slides, so please do get in touch. So I'll begin with work package 9, my own work package where we looked at the DC grid protection systems demonstrations. So what did we do? I'll start by saying a bit that throughout promotion, there was a lot of involvement across industry. So even within work package 9, I had myself, who's from a TO, we had manufacturers involved as well as universities, and all that helped us to really get a realistic testing. So within work package 9, it was effectively split into 3 work streams. The first one was about developing DC grid protection testing procedures and guidelines. And if you want to find out more about that, you can find deliverable 9.2 on the promotion website, where it goes into a lot more detail looking at what procedures you could go to undertake this testing. And then beyond that, the 2 other ones were related to the actual demonstrations themselves. There was the work done here at the National HVDC Centre, where our focus was on partially and fully selective fault clearing strategies. And within that, we looked at different combinations of breaker technologies and made use of real-world Ieds in our testing. To find out more details about the model, you could look at deliverable D9.1, where we outline how we've built up our test network. And then we had 2 demonstrators. Initially D9.3, which was an internal one, just to show the real-world Ieds working. So you can see the Mitsubishi Electric ID possibly at the back of that picture. And then Wednesday was the final demonstration, and given the circumstances, that was a virtual event. But the more information on that, we really delved into a full mesh grid with a fully selective scheme protected with these prototype Ieds in combination with all the different breaker technologies that been covered elsewhere in promotion. And then the final work stream was led by Supergrid Institute in Lyon, and their focus was on the non-selective fault clearing strategies. And similarly to my own work stream, there's a deliverable that outlines the test network and test procedures that they set up, and their demo was last Thursday. And similarly, there's more information about that online if you want to rewatch it. But between these two demonstrations, we cover all the different fault clearance strategies and look at all the different technologies that could be involved. And across it all, we were confident that we can find solutions that would work for this future grid. So the key takeaways are that we demonstrated successful operation of fully, partially, and non-selective protection schemes. So that's all the options, using the most realistic test cases possible without actually putting it on the real system. And throughout it all, the Ieds performed as you would expect, and it would be sufficient for use on the future HVDC grid. You can see a picture of the two Ieds that were used for the partially and fully selective testing on the side. So we had the prototype one developed at KTH within promotion, but we also had the industrial one provided by Mitsubishi under test, real devices. Throughout all of this testing, we looked at the interoperability of these different protection devices. So by mixing the technologies in one aspect, but with the supergrid work, they also started looking at the use of IEC 6150, which just would make it really easy to integrate into a broader network. As well as that, they developed a prototype system supervisor for non-selective. So again, this was going beyond something purely theoretical and actually implementing it on a device. And so that we could test these real-world devices, we've got real-time models for benchmarking the performance of Ieds, and this is across the two main real-time platforms, so RTDS and it's terrible. But we've got real-time benchmark models for different real-time platforms, and these tie in the work done elsewhere in promotion about developing realistic DC breaker models. And again, of course, we've got the test procedures that means that we can have a standard platform for judging all these different devices against. And so with that, I don't want to say too much more, and we'll get into the Q&A. So it's not just me answering questions, so please do ask. I will be joined with Marjan Popov from TU Delft, who really led the work on the test procedures. William from Supergrid Institute will hopefully be joining, who led the non-selective testing. I also have Ilke Jan from KTH, who developed the promotion ID. I think Fred Page from Mitsubishi will be joining as well, who was our main contact for the industry-provided ID. Got Durant Chafee from KU Leuven, who really helped within Work Package 9 of bringing the Work Package 4 protection design work in, and Habib from the centre, who did the heavy lifting of the modelling. So any questions you've got across the breadth of protection or demonstration across any of that, please do that. And with that, I'll now hand over to our quizmaster to introduce himself and start asking us your questions.
Yes, good morning. Can I have control of the screen, Jochen? Let me show my slides.
You good to go?
Yeah. It's this one. Is my screen visible?
Yep.
Okay. Yeah, good morning. So my name is Cornelis Plant, and I'm a consultant with DNVGL in HVDC Technologies in offshore power systems. And I'm also the coordinator of the promotion project, and it's my pleasure to be quizmaster for today. Do we have any questions in the chat, Jochen?
So far, we don't have any questions from the audience, so go ahead.
Okay. Well, we had a few questions that we received previously, so we'll go through. The first question, I think, is probably for you, Ian, which is, did integrating an HVDC circuit breaker in the existing real-time Kirknis-Murray Shetland model have any impact on the primary equipment ratings in the model?
Not that there, and that was one of the major risks for me with trying to use the replicas of Kirknis-Murray Shetland, which is a real scheme. Integrating the DC breaker models into that, it really ran the risk of it could just not work. And with the replicas, we didn't want to be making changes to them because we still need to be able to use them to support the real link. So it was quite pleasing and very reassuring, actually, that I could integrate a DC breaker model and I could still do all my normal operations. I didn't do a full factory system test, so I've not checked every single element, but certainly I could still do the normal startup sequence, dispatch power to whatever level, and do a lot of the normal functions. And even with integrating the big inductor that's needed for the DC breaker, when it energized the cable, you could see it took a wee bit longer to energize, but it didn't seem to trip any of the other protections. So I hadn't broken the pre-insertion resistors or anything like that. So without doing a full redesign work, nothing obviously jumped out as a big issue for integrating a breaker in. Okay, that's really good news. So it sounds like there's an indication that an HVDC circuit breaker and the protection system could be added to a DC grid as an afterthought, as part of an expansion, for example. But of course, it has to be studied more deeply. Yeah, and I think it would require some control changes, but yeah, and yeah. As we know, the controls are a minor part. It's not building things and putting bigger platforms in or anything like that. So yeah, all good news. Not a big capex investment. Exactly. Yeah. Thank you. We've got a question from the audience, I see. Okay. So what was the configuration and were the more onerous faults in the protection system performance? And in that case, I think what's that? Invite your yeah. Time to get some of
Yeah, so there are several different ways that we measure the system performance. So in addition to measuring the performance of the protection IEDs as a standalone performance, looking at the operation time of the IED, we use key performance indicators to look at the overall system performance, and this includes real power recovery time, reactive power recovery time. And so on this, well, in fact, on the case study network that we use, which is a 4-terminal extended Caithness array Shetland system, which was a mesh system because the focus of our work was on meshed topologies. It really depends on the fault location. So if we have a fault on the radial part of the system, of course, the converters at that end of the system can't recover correctly because they're isolated completely by a fault. Otherwise, it depends on the location of the fault and the circuit breaker and inductor configuration and how close it is to this particular circuit breaker. But in terms of overall performance, for primary protection, we see power restoration times in typically less than 100 milliseconds. And for backup protection in case of breaker failure, we see power restoration time in less than 300 milliseconds in all cases. So yeah, a reasonable performance, we would say. And the IEDs and the circuit breaker models operate correctly in each case. So encouraging results, I would say.
Okay. Thank you. Maybe I can add a question for myself to that. Did you also study which ones of those fault scenarios were the most onerous on the DC circuit breaker itself in terms of the stresses it gets subjected to, like the energy absorption or over voltages?
So we did monitor the peak current in the circuit breaker, the energy dissipation in the circuit breaker, but it wasn't really the focus of our study, which is more a system level study. When we did the protection system design, we chose, for example, inductors in series with the circuit breakers so that the circuit breaker was never exceeded its maximum fault current. So although we used the circuit breaker key performance indicators to evaluate that we didn't exceed the capabilities of the circuit breaker, actually because we did a good protection system design, this was just a verification, and actually we never exceeded the capabilities of the circuit breaker. So yeah, we do have the results to show which faults were the most onerous for the circuit breakers, but we didn't analyze them in detail.
And those can be found in the deliverables, I assume?
They will be published at some point, yes.
Yeah, great. Thank you. Okay, then we go to the next question. How flexible is the promotion IED, and what further algorithms could be implemented?
Yeah.
Okay, this is one for you.
Hello?
Yes.
Yes.
Yeah.
So the promotion IED, I mean, there's hardware involved, and currently the hardware is configured for sampling at 50 kilohertz. That means any algorithm that you would want to implement should be in the range, or should be working in the range of 50 kilohertz. So we've also tested at 20 kilohertz, and you could push it to 100 kilohertz. For anything above, at higher sampling frequencies, the hardware would need to be changed. And then if you still want to test with a real-time system, you would have to go from analog input to something optical. So that would require a larger hardware change, but it's a plug-and-play design, so I believe it's possible. And then for the actual implementation of algorithms, I mean, it's a dual-core ARM processor, so it's quite powerful. So I guess I'm confident that even a bit more computationally heavy algorithms could be implemented.
Okay, good. And could you maybe also comment on whether the types of signals and the right sort of bandwidth that you need for this this IVD are present or available in converter stations that have been built today?
So I mean, we've used a configuration where we assume a substation with 3 outgoing links with voltage and current measurements on both poles, positive and negative, and the bus bar. So now, I mean, there's none of those type of stations available out in the field today. So I guess I can't comment. But what would be necessary for the IED to operate is voltage and current measurements at 50 kilohertz. This is what we tested, at least, from all cable ends and the bus bar, both poles.
Okay, thank you. Then let's go to the next question. So the IEDs perform relatively fast in microseconds, although KTH is 3 times quicker. As the 2 IEDs have different responses due to hardware implementation and not due to the protection algorithm, which are the key attributes that define the bar in your tests? Is this a question for Fred?
Yeah. Yes, there are some panelists. Please unmute.
Great.
Oh, okay. Sorry, I haven't used the system before, so I was struggling to connect. I mean, the algorithms between them are slightly different as well. Ilka's KTH really does have a wider variety of algorithms. Our one's more specific. I guess it comes down to some of the difference in hardware implementation. I think we mentioned some of the slides or in our presentation earlier this week for 9.4. There is a redundant architecture, so that inherently takes more time with cross-validation of measurement and computation. So that causes some extra delay there, as well as the kind of level of hardware that's being used. So rather than being a prototype level, it's kind of industrial grade, which means that you have to take care of things like, you know, overheating and cooling when it comes to the CPUs. I suppose it should be viewed at a kind of a total system level. So there is some speed benefit there from Ilka's prototype that you can see, but when it comes into the context of the whole operation time, I think it's been demonstrated that this is kind of within the acceptable range, that you can still protect the whole system. So I don't know if that kind of answers the question.
Yeah, Brent, I think that's a point to highlight, because Ilka seems to average about 150 and your one's hitting about 500, but sorry, that's microseconds, but the limit is what, 2 milliseconds or something like that. So it's still well within the margin of operation that you need. And as you say, when you see the two of them side by side, I know which one I would rather be installing in a substation, because I didn't need to turn your one off to cool down every now and again. So yeah, I think that dual redundant architecture and just the realness is part of it there. But yeah, it's by far and away quick enough.
Thank you. Did you also test the promotion IED and the Mitsubishi IED together in the same simulation runs?
Yeah, not. Oh, sorry, Ian, go ahead.
I was going to say, yeah, but I think I might introduce Habib to maybe talk a wee bit more about the four terminal mesh that we introduced, and maybe just say about what we had where a little bit.
Yeah, maybe I could kind of just highlight as well that the I guess it's not just that we tested in the same network kind of in parallel at times. I'm not sure the latest results, but earlier in the year during one of the other webinars, we even presented some other results where you know, the two have been used together. So in some scenarios where we test breaker failure on one line, which was protected by one relay, that would be backed up by the other one. So kind of crosstalk between them to cross operate. So that kind of integration is, I don't know if it's called integration, but cross verification has been shown pretty well, I think. Interoperability. Yeah. Sorry, Habib.
Yeah, exactly. Okay, thank you. Let's go. I think we have time for one or two more questions. The next question that we had was, would you see the test procedures that were developed being brought into standards and code? This also, of course, touches the question of interoperability. And as we just heard, if you define the interfaces and standardize them well enough, you can achieve such vendor interoperability. But how do we bring this into the standards and codes? Mario?
Thank you, Cornelis. I think this will be a very challenging question for the future, especially because power system protection in HVDC, it's not only protection operation of the relay, but also it's a combination of the protection and the circuit breaker operation. Well, whilst for AC breakers, this is nowadays when we talk about the operation of the breaker, delay of several milliseconds will not be a problem. However, delay of several milliseconds when the protection operates and the breaker, this could be really a big problem. So what we have tried to address in these procedures was related mostly to the general protection principles on which every protection is based on. And these were like speed, seamless, reliability, all other aspects which are brought here. And we also touch this for a different type of protection schemes. So I think that this will be a good basement for the future standards, where still lots of testing must be done for particular protection. So I believe that these standards will be very useful. We derived formulas, and in the context of this, I have to point out that we used large experience of DNVGL from the previous testing of AC breakers, so that we have we really correlated with DNVGL in order to somehow start what from AC protection can be used in the DC protection. And I think that well, this can be really still worked. It should be still worked on this with lots of testing, and they could be useful for the standards in the future.
Okay, thank you. I think that also raises one of the key strengths of our consortium of having partners from both academia and industry working together.
Yeah.
And with that, I hand back to you. I think we've come to the end of this Q&A.
Okay.
Yes. Thank you. Thank you for your questions.
Ian, your presenter again, you can continue.
Can you share, can you give me the rights to share the screen?
You're good to go.
Are you able to see my screen?
Yes, but I think you're sharing the wrong window. That looks better.
This is the one. I put it in presentation mode, and there we go. Good, then we are ready to go now. My name is Renee Smith. I'm working for Kima Labs in the innovation part, and my function in this project was being the work package leader of work package 10. What I'm going to do now is I will present the results of work package 5 and work package 10 in one go, because they were a logical continuation to each other. And therefore, we will combine the results of both work packages in this introductory talk. Let me first show you the takeaways of the work package 5 and 10. We started in doing fault studies in HVDC multi-terminal systems. In order, we needed these to define the stresses on circuit breakers, because as you understand, it was our ultimate goal to test real size and real full power HVDC circuit breakers in the lab. Well, based on that, we have realized a complete test environment for HVDC circuit breakers. So that is available, and we had in work package 5 already 2 circuit breakers used to demonstrate that these circuits really do what they want to do, and they apply the adequate stress to the devices. Well, then, because an important part of the work packages was also to define a future input for standardization of circuit breakers, we have set up an experimental HVDC circuit breaker, because with that way we were completely free to measure and to study and identify the stresses on key subcomponents of these breakers. So this is also an important part of the work. And the result of that is an inventory of the non-standard stresses on standard components inside of HVDC circuit breakers. HVDC circuit breakers are complicated devices. A lot of standard components like vacuum circuit breakers, power electronic devices, surge arresters are used in a non-standard way. They get non-standard stresses, so they deserve attention from testing and standardization point of view. Well, then we defined, based on that, a test program to which each of the 3 partner circuit breakers were subjected to. So this is a common platform to make a level playing field for each of the circuit breakers involved in this project. Well, then, of course, the main part was the actual demonstration of the circuit breakers in the lab. Each of the 3 circuit breakers were assembled in the lab, and we have subjected them to the real power, and we have showed the world that we are able to make the circuits, and the circuit breaker manufacturers were able to demonstrate that their devices do as where they are designed to. Well, in the last phase of the project, we handed over the results of the test to IEC standardization work. There is now within IEC working group 64 is drafting a standard on HVDC circuit breakers, in which at least some parts of the inputs that were gained in the projects were used. On top of that, also 2 SIGRE working groups, one in study committee A3 and one in B4, are studying DC circuit breakers. Well, the key outcome is that the technical readiness level of the work was raised to a level of 7 for HVDC protection equipment, the primary protection equipment. And then the main conclusion of the work package is that fault elimination is no longer a technical hurdle for HVDC grid development. Well, this picture is showing you the proof of the pudding of which I was talking about. The key point in testing in opportunities to test is that we were able to design test circuits in an existing high power AC lab. So that means no major cost have to be made in erecting a specialized DC lab for doing the DC test. The trick is we do it with a low frequency of our generators, which means we run them into 16 to 30 Hertz mode. And that means we can create a pseudo DC environment. Well, with that, we are able to create, to replicate, in fact, all the critical stages of current interruption. To the right side of the screen, you see our most far-reaching test. It's a full power Hitachi ABB 320 kV 20 kA breaker. So this is the oscillogram of one of the tests. And here some data are provided. So the fault current that was observed to be interrupted is 20 kA against a counter voltage, a transient voltage of around 500 kV with an energy absorption of 10 megajoule. Well, last slide I would like to show you is on the demonstration, on the public demonstration we did. This is all about HVDC switchgear. So you see on the left top one, the active current injection of MEU, Mitsubishi Electric Europe there. As you see, that was in June last year. So that was the time when it was still allowed to gather some crowds in the lab. Well, at the next test, which we did in the beginning of this year with the ABB 320 kV breaker, you see in the back that could also be done. So a lot of attention was drawn there. In the lower left-hand corner, you see a test which was done in work package 15. So I will not talk about that, but also that was the beginning of the year. And then you see a test of the Hvac Hvac 80 kV breaker that was already under the 1.5 meter social distancing conditions, as you can see, because that test was just done a few weeks ago. Well, and with that, I want to conclude the introductory part. I hope it has raised some questions from the floor. So I would like to open the Q&A session by that, and I would like to ask to Kees, is there any question coming up from the floor so far? Because
let's give the floor some minutes to respond. Jochen, could you give me the screen control again?
We could maybe already start then with some question that came in before, Kees. So if the floor is, and then of course, if some questions from the floor come in, then we will come to them.
Exactly. Is my screen visible, Renee?
Yes.
Okay.
To me at least.
Then, yeah, the first question that we received was, what do you see as limitations in the assessment of circuit breaker stresses by transient system studies? And do you see input coming from measurements in the foreseeable future? And do we need these? I think this is for me.
Yes, well, you know, as I mentioned, work package, one of the important work that has been done in work package 5 is a part of system studies done. So the point I think that is being asked here, what do you see as limits of system studies as in defining the circuit breaker stresses? So if you could add a few words on that, that would be great. Yeah.
So I also coordinated work package 5. I forgot to mention this before, where we did this this study. And of course, these simulation stresses, or these transient system studies, are simulation studies, which are based on models. And fundamentally, the limit of such a study is how good a model you can get, how accurate this model is and reflects reality. And there's a couple of reasons why it might not reflect reality very well, thereby limiting the usefulness of the study, which is that there are a couple of different elements that need to be represented properly. One is the behavior of the circuit breaker itself, of course. Within the circuit breaker, especially the ones with mechanical breakers, there is a certain amount of stochastic behavior, which can be hard to model, and this has an impact, of course, on the stresses within the circuit breaker. And this is where I think measurements, especially measurements like we did in the short circuit laboratory, may be useful in validating the kind of stochastic models that we have there and the impact that they might have on the stresses on the circuit breaker themselves. Then there's also, of course, the aspect of parasitic elements, which are maybe not modeled properly or cannot be modeled properly in the models that we have, and may have an impact on the stresses on HVDC circuit breakers. And here again, laboratory measurements or maybe even field measurements can help to further fine-tune the models that we have and
okay.
the results of the simulation more reliable. And then the second last part is the AC grid itself. How do we model the AC grid and the state that it is in? This again, we'll probably have to learn from field measurements what the impact really is there. And the last part is, of course, confidentiality. So the models that we used for converters and the behavior of the converters, the protection, when do converters block, for example, has an impact on how much energy is dissipated in the DC circuit breakers. Information is quite closely guarded intellectual property by the converter manufacturers. So we've made assumptions there, which need to be, of course, revisited when the real vendor-specific models are available. But this could be solved indeed, of course, just by having a vendor-specific model rather than having to do actual measurements in the field.
Yes, what I would like to add is what we learn that we basically talk in this study only about electrical models. So we have seen a large array of PS cut studies, but looking at the real stresses to the breakers, as we learned, these are mechanical stresses, these are thermal stresses, these are plasma physical stresses. So we should not forget first that nature doesn't scale, and second that a lot of physics is involved here.
Yeah, certainly. And this is, for example, where the measurement work we did on modeling the behavior of HVDC surge arresters in the energy absorption can provide further validation of the models that we have.
Yes.
Okay.
I think some more questions came in before, so maybe we go to the second of these. You already projected them, but now it disappeared.
I think we have a question from the audience, so let's take that first. What is the size of the DC circuit breakers? I guess they are referring to the physical size. And
maybe
use this.
Maybe Nadu could face that, because he stood a number of times face to face to those real huge devices inside of the lab. So if you can comment on that, Nadu.
So the question is about the size of HVDC circuit breakers. Yeah, I think the right people would be, of course, the manufacturers. If I just talk from our experience, it also depends on the type of technology. So I think later maybe this can be answered by individual contributors from manufacturers, because they can also talk about their technology. I would say that, yeah.
There is a second question, Kees, you showed already, which is related to testing. So if we have Nadu online, it may be good that he could comment on that, about what is the maximum rating of HVDC circuit breakers that can be tested in the way developed in the project.
Yeah.
Maybe Nadu, if you can comment on that.
Yes, thank you. Well, that's a good question, actually. As you mentioned at the introduction, the method that we use for testing DC breakers in promotion was based on AC short circuit generators, which are available at most of the test laboratories. Well, there are challenges, of course. It's not straightforward. There are two challenges. One is to be able to supply the needed short circuit power as it would be in the system. That means you need to have the rated voltage and rated short circuit current from your supply, and then that also translates to energy later. So you have to be able to supply all those stresses to the circuit breakers. The second challenge is coming from the breaker itself. That means your test environment, the whole installation must be able to deal with the stress that is coming from HVDC circuit breakers, which is unique because most laboratories are not built for testing HVDC circuit breakers. But as we saw for 320 kV every breaker, there was around 500 kV TIV, which was coming from the breaker, which stresses the system components. So there are different components in this test method, like transformers, circuit breakers, spark gaps, some reactors are used. So all those components must be able to handle this stress which is coming from the breaker. So those are the limitations. If I just look at this method and look from the perspective of CHEMA laboratories, we could put together a lot of components in series, and we might be able to test HVDC circuit breakers up to 500 kV. That means our components can handle the TIV coming from breaker up to 800 kV. So those are the two challenges that you have to consider when thinking of testing HVDC circuit breaker in the method proposed. Well, the second question is about modular testing. Modular testing is definitely one of the ways out, especially as the rating goes up and above. As I said, we are limited to 500 kV DC circuit breaker. So beyond that, how do we test? I think we will opt for modular testing. But we have to be careful when we say modular testing. It depends on the design of circuit breakers, because modular testing doesn't mean that in all designs just cascading circuit breakers in series. If that's the case, maybe you can test 2-3 modules, and then you can see the sharing of stresses and the operation of each module at a time. But in some designs, modular approach is only on the current paths. So that means you cannot take out part of the breaker to test as a module, because some parts are rated for 500 kV, some parts are rated for maybe lower voltage because they are divided. So you have to be careful on the design when you say modular testing. Otherwise, it would be, of course, one of the useful approach to test HVDC circuit breakers.
Okay, thank you.
Thank you. So that's also different from testing valves, where modular testing is quite common.
Yes, in valves, you have the same components repeated one after the other. And there are also some kind of redundancies that you introduce. But here, the number of modules that you put in series in DC circuit breakers is not as large as those numbers in valves. So it's a different approach. It's a little bit tricky here. Well, if you prove a concept, you can work on modules.
Good. I would like to close this point and go over to another question. Case, can you check the floor? Or another question that came in before is on active current injection type of breaker. As you saw, we had one active current injection type from Mitsubishi Electric here. This is a type of breaker that is purely mechanical from the designing point of view. I would like to ask a project member from Mitsubishi Electric whether he can comment on this point. I'm not sure, because is Dr. Ito online? He did not log in as a panelist, as far as I can see.
Yes, he's online. I can give him the right one.
Please, yes.
Okay, hello.
You're good to go now.
Hello.
Hello, Dr. Ito.
Yeah. So the question about the active current injection breaker. So first of all, 160 to 200 is testing voltage conducted at the CHEMA laboratory using the double break modular type of DC circuit breaker. So the mechanical HVDC circuit breaker with a with current injection can be expanded to 525 to 600 kV level with a multi-break module with 4 to 6 units connected in series. So the advantage of mechanical breaker, it is designed with vacuum interrupter, which is well proven for more than 20 years at transmission voltage up to 200 kV. So also the mechanical breaker, I think that it's a significant cost benefit as compared to the HVDC circuit breaker technology applied with the many power electric devices such as IGBT. So that's my comment.
Thank you. I think it is clear. So maybe there is space for another 1 or 2 questions.
Yeah.
One question that came in what projects do you see appearing at the horizon, not only horizon 2020, for the HVDC breakers to ensure its further development? Maybe we could give the floor briefly to Hassan, Arman Hassanpour from Hitachi ABB. Arman, are you? I saw you are online. Maybe you can unmute yourself because we could briefly see you but not hear you.
Arman, you should be good to go. I can see his microphone is unmuted.
Hello?
Yes, please go ahead, Arman. We can hear you.
Hello.
Yes. Hello, Arman.
Yes, can you hear me now?
Yes, yes, yes.
Okay, finally. I think it's a bad connection, so I just stopped my webcam. Yes, yes. So the question was about the actually, what I can say here is basically the projects or the activities which are ongoing in North Sea and also in the Baltic Sea area right now can be the potential coming projects in the near future. So I should say that these 2 areas are the highest. They have the highest potential to have a pilot projects over there. And then in the next step, of course, is the inland connections. For example, in Germany, you can see now there are some activities regarding the corridor from north to south, and the DC breaker are also kind of enablers for those kind of connections as well. And then for the next part of your question, I should say that for sure there is no technical gap at all. As you know, the DC breaker, the hybrid HVDC breaker, is designed in a modular way, and you can treat it in a different ways. And there is no technical gap. But the thing which is missing here is basically the final pilot project. So the next step is to install, to have the possibility to install it in a real field and see the performance of the breaker. One question here is basically, do we really need a high current, or do we really need a high voltage for the breaker? It's quite customized design, so the current level can be adjusted based on the project requirements. But for sure there is no technical gap here.
Okay, thank you. Maybe a very short last question is allowed. Kees, can you?
It can be very short, within 1 minute.
Yes, I think this can be short.
Question is here.
Yes, so this is on the possibility of cascading multiple units of breakers. We saw in the Cybrake breaker that multiple units were used, so it seems fair that we ask Simon Nee from Cybrake to comment briefly on this.
Yes.
Simon,
Do you hear me?
Yes, we do.
Very good. So yes, our breaker design is purely modular with independently operating modules. So of course it's difficult. I cannot say that it's ever easy to realize anything large and physical, but from our point of view, there is no technical problem in series connecting these modules. It's very similar to how an MMC converter would be built. The modules are operating entirely independently, and the stresses on the modules are only dictated by the current through them. The thing that is dependent on the design of the breaker is the auxiliary power to each module. That is of course something to consider, but it's a problem that has been solved in other
Yes.
other equipment. So yes, the obstacles are of course that it's simply difficult to design such a device, but the technology allows it right away.
Okay.
I think.
Thank you, Simon. I think when I look at the clock, it's time now to close. If there are some other questions, Kees, please send them to us so that we can answer them offline in a good way.
Sure.
So I thank you for your attention and for your contribution to the discussion, and we change over to Ian, I guess, or straight away to work package 15.
Ian, I handed it over to you. Let me know if you would like somebody else to continue.
So, good morning also from my side. Could you already see my screen?
Yes.
With the presentation, yes. Okay.
Yeah, you're in presenter mode right now. You would need to go full screen.
No.
Perfect.
Yeah. So, hello again. My name is Uwe Richard. I'm with ABB Hitachi since more than 20 years now, and I'm also leading the work package 15. And it's a pleasure for me to give you a short overview about that, what we have done in work package 15. And let me start directly with a summary of one of the main targets of work package 15 we have reached in the past. You could see here on the right side a test setup of a gas insulated switchgear for HVDC rated for 320 up to 350 kV. And that was one of our main targets, to increase the technology readiness level for a gas insulated HVDC switchgear. And maybe most of you know that a gas insulated switchgear has some advantages compared to air insulated switchgear, and that is mainly related to the size. So a gas insulated switchgear could be installed with a much higher degree of compactness, and we can finally say that we can reduce the size for the HVDC switchgear using gas insulated components by 70 to 95%, and that is of course very interesting for platform installations where the size is the main restriction
for use of switchgear components. So we have made for that a long-term test, because there is only a limited experience with this kind of new technology, and this test was finished. And you could see on the left side also a picture of one of the demonstration events for the HVDC GIS. So finally, we can say that we can expect that an HVDC GIS components or a GIS installation will have equally long lifetime compared to that what is known from AC switchgear. Some more words about the installation itself. So we have, of course, there was a request or a demand from users, from utilities, from regulators to perform a long-term test and so-called demonstration test or a prototype installation test. And for that, to perform that, we have prepared a test setup which contains all typical GIS components like a bus ducts, high voltage DC connectors, disconnectors, earthing switches, fast acting earthing switches, bushings, and current voltage measurement sensors. And to keep in mind the long time experience, we have increased the test voltage by 20%. So the test voltage for this long-term test was 420 kV. And moreover, we have injected the current, what you could see here, using conventional AC current transformers. So we had at the same time also an AC current of up to 4,000 amps running in the test pole. You could see here the complete test procedure. So we have started in 2018. So after roughly 50% of the promotion project was already finished, but we started with the work package 15 in 2018 with preparation of the test. And the main test is what you could see here, consists of in total 6 blocks with a continuous DC voltage, and each block was roughly 60 days long and was completed with a superimposed lightning and switching impulse test and with operations of the switching elements, so the disconnectors, earthing switches, and fast acting earthing switch. The difference between the blocks was a DC voltage, so the polarity plus or minus, and also the load. That means one blocks were performed without current and other ones with high current, so 4,000 amps. So the test started in the beginning of 2019 and was finished in July 2020, so some months ago. Again, some words about the key conclusions from our work package related to the DC GIS. So we have increased the technology readiness levels to 8 for the HVDC GIS equipment. We have prepared recommendations for specifying gas-insulated HVDC systems, and also testing requirements, procedures, and methods were developed based on simulation analysis on real HVDC onshore and offshore experiences and based on a CGRE work. We have performed these long-term tests on a full power HVDC GIS according to the developed test requirements and procedures. And of course, the results were also used to improve the models and develop the understanding of failure mode. And moreover, work package 15 activities are also aligned with ongoing CGRE activities. And we have also prepared and contributed to standardization work in CGRE and in ISC. Yes, that was a short overview about the major part of work package 15, and we can go now directly to the questions. For that, we have some more people on the panel list. So Hong Hee, she is from DNVGL and was responsible mainly for the test itself. Nerju Belda is from KEMA Labs, you know already from the first session, and Michael Gatsche also from Hitachi ABB Power Grids. So So now we are ready for the Q&A session, and I will, I think, hand over directly to Case. Yes.
Yes. Johan, can you give me my screen? Yes. Here we go. So we received some questions. The first one is it necessary to repeat the test if the current rating increases to 5,000 amperes? And what if the rated voltage increases to 550 kV? Michael, I see you've come online.
Hello. I will try to answer the question. Maybe as a general statement, as Uwe mentioned, it is a non-mandatory test. The aim of the test is to increase the technology readiness level of the technology and to precede actual real-world experience with HVDC GIS. So from a purely standardization point of view, it would not be necessary to repeat the test. But of course, we can give some technical comments on these two questions, an increased current rating or an increased voltage rating. When we look to an increased current rating, for example, to connect, let's say, two cables in parallel or things like that to increase the current rating, this is not such a big change as long as the temperature difference along the solid insulators stay the same, and we could ensure this by a changed design of the current path, and it can be proven, for example, with the temperaturized test that the temperature difference stays more or less the same, and that would have much less effort than this prototype installation test. So the technical recommendation would be to not repeat the test for an increased current rating. When we increase the voltage rating from 350 to 550, for example, this would then we would have a different geometry and newly designed solid insulators in the GIS. And in this case, the technical recommendation would be to repeat the test, because then we can have, let's say, a different balance of the different DC effects in the insulation, and then it would be advised to really repeat this test for the 550 design.
Okay, thank you. Next question is, why was an SF6 to air bushing used instead of a cable termination? And the second question next to that, is a cable termination available?
I would also try to answer this question. We've designed the HVDC GIS to be able to operate with overhead lines and also with cables. So we have the SF6 to air bushings available, and we also have a cable termination available. If we purely look at the GIS, if it is specified for connection to an overhead line, we would have higher impulse over voltages, for example, the lightning impulse over voltage. And so from the HVDC GIS point of view, we wanted to include let's say the hardest stress in the test, and this is why we tested this with the bushing. And that's the reason why the test was performed the way it was performed. And as I said earlier, we would have a cable termination available. It's also qualified.
Okay, thank you. Then we go to the next question, which is, what are the biggest challenges in performing these long-term tests for HVDC GIS? Nadu, I see you've come online.
Yes. Hello again. I just want to say a few words before Hong might add a bit there, actually. Well, of course, it's as you mentioned it here, it's a long-term test. That means you have to prepare for that. That means you have to set aside a lot of space that you cannot use for 1 year. I think the challenge is the practical aspect of it. For example, the tests have been divided into 6 blocks, each block lasting for 60 days. That means the test setup must be continuously running, well, at least without interruption, or if there is interruption, then you have to fix it quickly and compensate for the lost time. So that was, I think, the challenge, to keep monitoring for all the 60 days in voltage, current, and also in temperature. And of course, at the beginning, also to agree on the test requirements and then try to design a test circuit that can fulfill the requirements was also the challenge. I think Hong might add to this because she was the one who actually performed the test. Yeah, thank you from my side.
Thank you, Nadu. Hong? There you are. We cannot hear you, Hong.
You're unmuted, Hong, or you should be able to unmute yourself now.
Oh yeah, it's okay. Yeah. Actually this test, as Nadir says, it's challenging. We need to continue for 60 days because you need to build up a DC field stable. This is really challenge. For instance, we can remote control via our mobile phone. I remember during this 1 year test, every time I cycle, before I go to sleep and before I wake up, you check the mobile phone first if cycle continued. So then you can imagine it's really challenge. But I think technically also challenged because I think this is first time such a large and full-scale DCGIS long-term test. Then how to say, we technically we also need to understand how to build test setup, understand test procedure, but also, you know, case we also bother you very much because from a support point of view, financial planning, execution, you also need to coordinate with all the members. Then I think this is really teamwork, also the challenge. So eventually we finished successfully testing. Object also passed the test successfully. I think this is really good. Our promotion teams working package 15, and also from a promotion from case the administration support, and also very important is schema testing team. It's really during, if in case weekends we need to go there, there's a team will be support. I think that's why it can be successful. Challenge, but really valuable experience. Okay. This is my
So not only did we prove the reliability of the GIS, but also of the monitoring systems and of the team members.
Indeed. Yeah.
Okay, let's go to the next question. What are the differences to HVAC GIS type tests? Michael.
Yes. So the major difference is that with the dielectric tests, we have added superimposed impulse voltages. That means that you do not just test, let's say, first the AC withstand and then switching impulse or lightning impulse withstand, like it's done in AC, but you have the DC and at the same time the lightning impulse and the switching impulse superimposed. So this makes the test a bit, it's more effort for the test. I think Hong can confirm this, that because you need the two generators at the same time, you need a divider that can also measure it at the same time. So this is a major addition, and another addition is the insulation system test, where you combine the thermal and the dielectric stress to really get the insulation at to the critical point in the DC, where you try to reach the DC steady state. And that is an addition, and it's a quite long test, and it is also more effort because you combine the high current and the high voltage testing. But of course, if we look at the GIS as a complete product, there's also a lot of things that are identical. For example, a gas tightness test, a mechanical endurance test for a disconnector, or a short-time withstand current for the components. They are basically the same, and maybe in some cases we can even take results from a AC GIS that has a similar design.
Thank you. We have time for one last short question, I think. Let's see. What is the current status of standardization of HVDC GIS? I think you probably know best.
Yeah, I can say some words about that. So I have already mentioned that there is a SIGRE group running, dealing with the dielectric specification of a DC GIS. And this group is close to the end, so we have a final draft now ready, and it's expected that we have the technical brochure, let's say, in 1 or 2 months from today. And based on that, we have decided in ISC that we will build up new working groups, and there is already one running dealing with switchgear, HVDC switchgear, with general requirements for HVDC switchgear. And the second one is already confirmed, dealing specifically with HVDC GIS, and the first meeting is scheduled for the next some weeks. And because I'm the convener of this group, I will already mention that we are looking for more members. So we have at the moment 7 members. So it would be nice to get more people involved in these activities.
Okay, great. So the first standards are on the horizon then. Thank you, Uwe. And I think we hand over now to work package 16.
Okay, perfect. And let's see if I can share my screen. That looks good.
You should be presented now, Philip. Yep.
Yes. And I think you should see the right screen.
Perfect.
Okay, then also from my side, a very welcome to this breakout session. I'm presenting you our results in work package 16 on the DC grid and offshore wind farm control, especially the compliance evaluation and the demonstration here. Okay. My name is Philip Ruffing, and I'm working as team leader for the team DC systems at the RWTH Aachen University, where I also did my master's and my PhD in 2015 and the PhD this year. And within promotion, I was mainly responsible for work package 16. So I was leading work package 16, but I was also helping doing the model development in work package 2, and I was responsible for the full bridge-based protection strategy, so the full blocky converter-based protection strategy in work package 4, but also in work package 2. So let's start with a very brief introduction on our pre-recorded presentations regarding the DC grid control and offshore wind farm control, compliance, evaluation, and demonstration. So you can see also here our partners within the work package who all actively contributed during the session. But myself, then Professor Ramon Jimenez and Dr. Yang Tao Yang had the pleasure to present you all our results in the breakout session before. So during the breakout session, I gave a brief overview about the demonstration of the controllability and interoperability of offshore MTDC networks using a multi-terminal HVDC test bench, so power hardware and the loop test bench. And our results, our test cases comprise the operation of different grid configurations, the interoperability between MTDC networks and offshore wind farms, as well as the fault handling in HVDC grids, and the demonstration of AC grid support concepts, also using offshore, the offshore grids. In the second part, Professor Ramon Jimenez gave you some insights on the control hardware and the loop demonstration using offshore wind farms connected to shore via direct rectifier units, and regarding the black start capability of offshore wind farms, which were also directly connected to shore via AC cables. And these demonstration comprise, on the one hand, the integration of control hardware, of physical control hardware, so wind turbine controllers. These were implemented on DSP controllers, and a commercial protection relay. And thereby, these were embedded into a real-time simulation test bench. Oh, sorry, I will maybe include this, then you can see yourself. And these were then also integrated into a real-time simulation test bench. And last but not least, since the offshore wind since offshore collector grids are 100% converter-driven networks, without, for example, the damping of synchronous generators, it is very important to also investigate the stability during the early stage of the project. And therefore, Dr. Yang Tao Yang presented you the process on how to assess stability in such grids in an early stage, and therefore he gave some insights on how to characterize HVDC, but also wind turbine converters by measuring their frequency-dependent impedance, and then how to assess the stability in the grid using, on the one hand, frequency domain analysis, but also some time domain validations of this method. And before we dive into the Q&A session, let me quickly summarize our main outcomes. And regarding the Hbdc grid demonstration, we demonstrated that the control and protection concepts which were developed in our technical work packages, so work package 2, 3, 4, that these could be applied to multi-terminal DC grids, and that these actually worked out in our small-scale demonstrator, but also matched, so the results matched very well with the full-scale simulations. And with this, we could increase the overall confidence in them. And moreover, we showed that it is possible in that sense to operate HVDC grids in combination with wind power plants, which can be either in grid forming or in grid following mode. And this we did by the power hardware in the loop demonstration. And last but not least, we carried out first physical demonstrations of a DC bypass breaker concept and the full bridge protection, or the protection based on full bridge converters within a multi-terminal test bench. So for sure, a low scale or a downscale multi-terminal DC grid test bench, but these were kind of the first demonstration of these concepts. Regarding the DIU connected offshore wind power plant, we demonstrated that the grid forming wind turbines and the corresponding controllers can be tested using the compliance evaluation procedure, which was developed in work package 3. And this was carried out in the control hardware in the loop environment. And therefore, on the one hand, the HVAC black start capability and islanded operation of the offshore wind power plants was demonstrated. And as already said, the connection of offshore wind power plants via diode rectifier units. And therefore, we had on the one hand multiple academic wind turbine controllers. These were implemented at the UPV in Valencia and implemented on different DSP controllers, integrated into the real-time simulation. But we also investigated one commercial wind turbine controller, how this would behave in these kind of similar situations. And this was carried out at the NVIDIA in Harmonic. And overall, it could be shown that it's very relevant to respect these number of DSPs or real converter cubicles as well, to respect all the relevant challenges here. And last but not least, for the stability assessment, our main conclusions was that the developed impedance measurement method worked very well, and we therefore, on the one hand, verified it using we measured and compared the impedance of a real wind turbine converter, the same one as also used in the previous case. So here, the commercial wind turbine converter of 1 megawatt compared with its control replica. And here the results or the impedance measurement matched very well after the model was adjusted accordingly. And the same was then also carried out for MMC converters, for using for sure our laboratory scale converters, but also here their corresponding control replicas. And overall, with this we could show that it's very important to respect a sufficient modeling detail if you want to carry out these impedance measurements in a simulation-based environment. And here, for example, a control hardware in the loop setup would be an applicable way to go forward. For sure, if you have a very good model of the system, you could maybe also do it just with a simulation, but this is very tricky, as we also saw doing a pierce cut comparison, for example, with the corresponding model. And for all of these demonstrations, we carried out physical or online demonstrations. So physical demonstrations last year for more for the wind turbine side, and this year for the control of the HVDC grid, but also the diode rectifier control. This was carried out this year during an online event, and you can find these on the website if you want to follow them. And also we contributed by our work, for example, to the working group C4.49 for the multi-frequent stability of converter-based systems, and had during the standardization process in work page 11, and also tried to increase the overall confidence in the developed control concepts, and that would maybe lift the TRL of the control concepts a bit, as you will see during the next presentation. So all results have been published in D16.3 and will be published partly in D16.4, which will be online on our website end of this month, beginning of next month. So here, please be tuned for that. And after this brief overview, let's now come to our Q&A section.
Thank you, Philip. So we do have some questions. The first question is regarding grid-forming wind power plants and their black start capability. So within the breakout session, black start has been demonstrated for AC and diode rectifier unit connected offshore wind power plants. But what would be the challenges for VSC connected grid-forming wind power plants regarding their black start capabilities?
So therefore, maybe we switch on the microphone from Ramon. He will be perfectly suitable to answer this question.
Ramon, you would be good to go now.
Hello?
Yes, we can hear you.
Okay, excellent. So, thanks a lot for the question. That's I was going to say $1 million question. I think there are two issues mainly. There are technical issues and also create a business case for that. So those are two independent issues that are little by little, I think they are going to be aligned. From the technical side is that we have quite a lot of grid forming solutions, and all of these grid forming solutions have a relatively low operational experience. So that's something that is got to be sorted out, and especially during black start, which is a particularly challenging scenario. So we have to make sure that when we get all this energization of large transformers and large cables, we keep the whole system happy within the limits, and that we don't have interactions between the wind turbines. So that's something important. My feeling is that grid forming applied to black start or to islanding operation. Islanding is also very important to keep the auxiliaries of the offshore wind farms when there's a problem on the export cable. My feeling is that those probably will be some of the first industrial applications of grid forming, only for one sense, because both islanding and black start are emergency operation, so you can certify easier the wind turbines for this kind of operation, and then move back into traditional controllers. So this certification should be somehow easier. But again, and also in these two cases, it will be easier to find out a business case, because for islanding operation, the business case is clear. For black start, we have to go through a qualification process. We have to get all the TSOs aligned on the requirements and how we are going to qualify the wind turbines for that. But once they are qualified, we can get into this black start market. So the challenges, the technical challenges are really something that can be worked out. I think the main challenge right now is to align the business case with the investments that are needed for the development and certification of these capabilities.
Thank you, Ramon. I think that holds not only for grid forming converters, but actually also for HVDC grid technology.
Yeah,
So,
yeah, that's right.
Good reminder. So the next question that we have is regarding harmonic stability assessment. So what was the main challenge regarding the impedance measurement of commercial wind turbine generators? And what would be the required level of simulation detail to achieve close to reality impedance measurement in simulation?
Okay, then this question I would like to forward to Yong Tao. He should be also with us, I guess.
Yep, good to go.
Perfect.
Hello, can you hear me? Yes. Yeah, thanks for the question. Yeah, for the major challenge we see for the wind turbine, we have performed that in both control hardware and the power hardware in the loop testing for the impedance measurement. The major challenge is actually to get the proper signal, and also to have the right simulation time step. Yeah, if you have a too large delay due to or too large time step, it will pollute your measurement results. Also, when it goes to higher power, higher frequency range, there, especially with power hardware in the loop testing, we experience both the noise, but also the instability of the system. Keep in mind that's a 1 megawatt power pushing into our lab, so that's a huge challenge. I think happily my colleagues have done that, handled that very well, and we got again valuable validation of our model, both theoretically model and control hardware in the loop model. Yeah, that also goes to the required level of simulation details. I think the important thing is to have sufficiently good time step, but also you should reproduce or reserve the whole loop, the whole time delay. Otherwise, you will get too optimistic results. Yeah.
Okay, thank you, Dr.
Yep, thank you.
Let's go to the next question. The next question is relating to the NMC test bench. So the question is, what were the main problems that you faced when connecting simulation and electrical hardware in the power hardware and the loop setup? I guess that's for you, no, Philip?
Yeah, or I would actually like to forward the question to my colleague Fisnik, who carried out most of these tests. So he should be also the one to answer them.
Yep, and good go.
Hello?
Yes, we can hear you.
Hi. Yeah, thank you for the interesting question. Well, initially a challenge on its own was to implement the control algorithm that we developed for our full-scale simulated models with our MMC test bench. We had to basically scale down our simulated model to a lab-scaled model, then implement it in a digital twin simulation of our, let's say, a single MMC station, and after successfully testing it with the simulated lab-scaled models, also implemented with the MMC test bench and successfully testing it with the MMC test bench itself. Regarding the connection between the simulated part of our overall system, let's say the AC systems of the offshore wind farms, with the MMC stations, which are in hardware, the main challenge was to design the proper power hardware in the loop interface algorithms, such that the interaction between the simulation and also the hardware part of the network was stable and was reacting in a proper way as anticipated.
Yeah, perfect. Thanks. So it's here still a major challenge also going into fault studies, for example. That's relatively tricky because you have some so steep changes somewhere in your simulation that this has to be traveled through the PHL interface. So looking forward also to work on this in the future.
It is also, for instance, a major challenge also for very weak networks if you are trying to implement them with a power hardware in the loop interface itself. Yes.
I think this also again highlights the fact that, as we've heard also for HVDC circuit breaker testing and gas insulated substation testing, that designing the right type of test environment is to be able to prove that the technology is mature at all is equally important as designing the technology itself.
Yes.
Thank you for that. We have time for one last short question. This one is relating to the small-scale protection demonstration. What was the main difference between the full-scale simulations that you've done and the tests carried out in the small-scale to laboratory-scale demonstrator? And is it possible to extrapolate the results from the small-scale to the full-scale HVDC networks?
Yeah, it's a tricky point. So from our point of view, the control always saw the same challenge. So if you have a full-scale simulation or a small-scale physical test, the control was always exactly the same, and the control never knew to what it was connected. And so by layering more or less all the different test levels, so a full-scale simulation, a small-scale simulation, and the physical test bench results, we could achieve, like, let's say, test as good as we can go in such a setup. But there's one main difference. It's very tricky to design such a setup with very low resistance. So all your components will have like higher resistance than it might have in a physical system. So for example, let's say we have, so for example, we implemented a small scale HVDC circuit breaker from KTH into the system, but the forward voltage of this circuit breaker is relatively high compared to a real circuit breaker. So here it's then the question, we had to adjust the models to reflect then also the system properly, and we could show that the control works more or less, let's say, in both conditions. So on the one time with the additional resistance included, and one time without the additional resistance included. But overall, we are very happy with how the results came out. But for sure, there's this difference between the resistance in both systems, like a proper full-scale system and a small-scale system.
Yeah, again, also underlining the point that Renee made, that high voltage doesn't scale.
Exactly. So for the control, it might scale a little bit.
Yeah.
But and I think by using such tests, you can increase the confidence in the control overall. But there's nothing like a full-scale test.
Yeah. Okay. Thank you very much, Philip. So then we move on to the next part, where we tie actually together all the three different technologies by assessing what has been the advance in the technology readiness level that was made by promotion. So Rian and Jayang, the floor is now yours.
Rian, you're now presenter and you can go ahead. Rian, hello, can you hear us? Yeah, you're sharing the wrong screen so far, I think. You can see your Microsoft Teams.
So good morning, everyone. I hope that I'm on the air now.
Yes, we can hear you. Perfect.
Great. Thank you very much for your presence, and it is a pleasure and a privilege to present you today the technology readiness levels, as we have developed and adapted the technology readiness level assessment technique as it existed before to the T&D industry. I have done that together with my colleague Jayang, and Jayang will present our final report and findings in the next minutes. So I'd like to transfer to Jayang now, please.
Jayang, you're now presenter.
Good morning, everyone. Is it possible to see my screen now?
You can see your desktop so far?
Yeah, just.
And you would need to switch to full screen. You're in presenter mode.
Okay, yeah, just.
It's up in the display settings. Yeah.
Okay, I believe now you could see the full screen, right?
Excellent, yep.
Okay, good, excellent. So yeah, good morning, everyone. This is Jayang. Together with my colleague Rian Marshall, we were working in the last stage for promotion to have a TRL, Technology Readiness Level Review, on the technology investigated in promotion, or let's say for the meshed HVDC transmission network. So today I'm going to present our work regarding TRL review. Just briefly introduce introduction about myself. Now I am, this is Jayam. I'm working with as a consultant for the transmission and distribution technology in DNVGL. So today, I'm going to present the TRL review in the meshed DC transmission network. But why would we like to review the TRL of the meshed HVDC network technologies? The HVDC technologies are the enablers to shape the offshore HVDC grid. This has been shown through the previous presentation by other working package leaders. So in other words, the offshore HVDC grid planning is enabled by the technology maturity of novel components and technologies. So in order to determine the HVDC technologies and to compare the HVDC grid alternatives, ideally, the maturity level of each technology is quantified. So TRL, the technology readiness level, is a systematic method to quantify the technology maturity level towards the industrial deployment. So then, yeah, in the following presentation, we will see what is the TRL and the adapted TRL, and what is the TRL of the promotion technologies. So we're going to see the TRL scale and the definition, as well as adapted TRL to transmission and distribution industry. In the next, we will see the TRL being assessed for the technology in promotion, and also for a better, a bigger overview, we also have a look at the TRL for other HVDC projects in EU and China. So the technology readiness level was the scale was originally developed by NASA for measuring the maturity of a certain technology. It was introduced into the EU-funded project Arena in 2014 as part of the Horizon 2020 framework program. The Horizontal 2020, let's call it H2020. The TRL H2020 is a generic definition. So in order to apply the TRL skill to transmission and distribution technologies, the generic TRL definition needs to be adapted, or let's say customized. Especially a distinction is made between a hardware-based technology and algorithm-based technology. So basically speaking, the TRL skill described the development path of a certain technology from an idea, then going through modeling, experiments, demonstration, qualification, and finally become a commercial competitive product. So each TRL level represents a certain development stage. We have customized the TRL definition to transmission distribution industry. The adapted TRL skill is aligned with the T&D product development process towards the qualification for commercialization. Since nowadays the standards and norms for the offshore DC grid are not yet ready, so TRL review or the skill is a really helpful tool to quantify the stage of a certain technologies. And moreover, in the T&D industry, the technology are generally based on either algorithm or hardware. For example, the HVDC circuit breaker is a hardware-based technology, and the HVDC grid control is an algorithm-based technology. So therefore, we refined the TRL technology, refined the TRL definitions for algorithm-based and hardware-based technologies. Both of them, they start with formulating the concept and then followed by designing the models. For the algorithm-based technologies, the model will be validated by simulation, and especially for desired applications. And then the electronics hardware will be implemented to realize the algorithm. After being demonstrated with functional stress, it can go for the commercial manufacturing. And for the hardware-based technology, the materials and the physics all need to be modeled and simulated. The physical experiments are also required to be carried out. And then the prototype of the physical hardware need to be built up. So after being demonstrated with physical stress, it can go for the commercial manufacturing. So far we have an overview about what is the TRL skills and what we have done to adapt the TRL skill, the H2020, to transmission and industry distribution industry with refining or defining the algorithm-based and hardware-based technology. So with the adapted TRL skill, we could go to apply it to the 4 enabling technologies for the offshore meshed HVDC grade in promotion. Actually, let's say the TRL level of each technology has been already given or presented by, in previous presentation mentioned by the other group leaders. But here we are going to have a look at how the TRL review are acquired and briefly. And in the end, we are going to see again all of the 4 technologies with their TRL level. So we start with the HVDC circuit breaker, which is hardware-based technology. And as already presented by Renee, that there are 3 circuit breakers from 3 manufacturers being demonstrated in Kima lab. And here we will take the hybrid circuit breaker from ABB as an example. So later on for the other technologies, we will just really fast go through all of them. For the hybrid circuit breaker, DC circuit breaker, within the scope of promotion, there are several working groups have contributed to the development of the circuit breaker. The investigation started from analyzing the model, and then several work has been done by different working groups, such as formulating the concept, the control strategies, requirement of the circuit breaker, and also developing the real-time digital simulator models, unit test, and short circuit test, etc. And in the last step, the DC short circuit current breaking capability of fully rated and fully integrated prototype of the hybrid DC circuit breaker was demonstrated successfully in system level, which is justified as an advance to TRL 7. So the test project here was manufactured during using the regular production process and implemented using an existing fully qualified valves support structure design. So this is like the growing path of regarding TRL of the hybrid DC circuit breaker. So the same method was applied to assess the TRL of other 2 circuit breaker, the Hvac and active current injection circuit breaker. And both of them result in a TRL 6. When we have a technology from different suppliers, then the TRL level of this technology will be determined by the highest TRL level among the different suppliers. So therefore, here the TRL of the HVDC circuit breaker is reviewed as a TRL is reviewed as a TRL 7. Yeah. So then we look at fast the HVDC grid control, which is an algorithm-based technology. So we have accessed different aspects, or let's say sub-technologies of the grid control in a meshed DC grid. So yeah, so with the demonstration of the control in meshed DC grid with the MMC test bench demonstrator, the TRL advanced to level 6. For the other 2 sub-technologies, the grid forming cluster control and also the converter control during the fault clearing in the meshed DC grid, they all acquired a TRL 6. So hereby we have the TRL of HVDC grid control as reviewed as level 6. For the HVDC grid protection, we reviewed the selective fault clearing and the non-selective fault clearing with 2 different technologies. So for the fault clearing, selective fault clearing, by integrating the DC circuit breaker modeling, the DC protection development, and IED, and also the converter control and protection replica, the system prototype demonstration advanced the TRL to a level of 6. And for the other 2 non-selective protection, where they acquired a TRL 6 and 5 respectively. So as a result, the TRL of HVDC grid protection is reviewed as a level 6. The HVDC gas insulated switchgear GIS system for use in the HVDC transmission has been under development by many manufacturers for several years already. So the maturity level of the HVDC GIS is relatively high when promotion started the investigation. However, there is no international standard for the specification requirement and test procedure for the HVDC GIS. The investigation of it in promotion provide specification and the long-term test requirement, which helped to advance the TRL level. So the aspects investigated including the GIS with SF6 and SF6 alternatives, as well as a new PD monitoring and diagnostic system. And the HVDC GIS prototype system has been demonstrated in promotion through a long-term test, which bring the GIS to a TRL level of 8. And for the other 2 aspects, they were reviewed as a TRL 5. Therefore, in the end, the TRL of the HVDC GIS system is reviewed as 8. So far we have reviewed the TRL levels of all the enabling technologies in promotion. Apart from this, there is also an interesting topic, which is the interoperability considered in promotion. So here, this is the TRL review of the interoperability between different converter technologies. So yes, there are some more information, but considering the time, we're going to go further. And in the end, we also have another look at other related HVDC project, either within EU or also in international worldwide, for example, in China. And this project also have investigated the HVDC technologies, which could also provide us some view about the development status of HVDC technologies worldwide. So here you could see the map presenting the status made by the other EU project made by promotion, and also what is happening in China with the HVDC project. So yeah, so far we have viewed about the TRL itself, the TRL of the technology in promotion, and also some other related project. So yeah, now I think we go to the Q&A session. Any question, please feel free to ask.
Okay, so I hand it over to you.
Yeah.
Yes, thank you very much for a very interesting and comprehensive presentation. Do we have any questions from the floor?
No.
Okay. Then maybe Jayang, I have one question for you.
Yeah.
At what TRL level can you consider technology ready enough for implementation in, for example, a full scale or a real high voltage system application?
Well, please, sorry, please finish your question. I interrupted you.
Sorry, no, I finished it. So at what TRL is a technology ready enough for application into a real transmission grid as a pilot or even a first real part of it?
Okay, in my point of view, I have to say that it's also different from region to region. Actually, I showed this in the last slide. Basically speaking, when the technology reach a TRL level 9, which means the technology is already mature, ready, and it has to have already gone through the qualification, the standard, and the manufacturing process has already been established and optimized. So this is TRL 9. When the technology reaches TRL 9, it means it's already mature and ready for the market. So then by any time, you could approach to the supplier or manufacturer to buy and to apply it. So this is basically, theoretically speaking, it should be TRL 9. However, on the other hand, it's not that easy to view or to give one value of TRL level to a certain technology. For example, I mentioned about the market in China. Actually, in some HVDC project, for example, the Zhangbei HVDC project, over there were already the HVDC circuit breaker installed and already commissioned. And those circuit breaker, they have passed the type test. However, the type test is somehow different from the TRL 8, which means the international standard or norms, because those tests have been done in the manufacturer's lab, and what they need is to have a third party to witness the test. So according to our TRL scale, yes, they haven't done the test according to the international standard or qualified. So they shouldn't have reached to a TRL 8. However, on the other hand, those circuit breaker has already been commissioned, and so far during the operation, it works well. So in this sense, we could see that they are already like being applied. The only thing lack of maybe is just the operationing experience. So still, we could consider TRL 8 or 9 for this HVDC circuit breaker. Okay. So yeah.
And so in the interest of time, I think we need to round this off now. So I hand over back to the chair of the session, Ian, to close it. Thank you, Diane.
Welcome.
Can you see my screen? What's the button?
That looks good.
Do you see me now? Excellent. So yeah, just a brief conclusion. So thank you to all the presenters today and the panelists for joining, and thank you also to the audience for coming and listening, of course. So just a concluding remark. I thought I was about to get kiboshed there by the TRL assessment, but no. I think hopefully you can see that there's no technical showstoppers for a multi-terminal HVDC grid. So it was mentioned earlier about the outlook in the North Sea and the Baltic Sea. When you look at those upcoming wind farms that are far offshore, you could justifiably draw yourself a nice mesh DC grid and go to the market, ask for some HVDC circuit breakers with some protection Ieds to go with it, with an overall grid control and some GIS to shrink it down into something you might want to put on a platform. And you can see from the work done here that it's not TRL 9, it's not business as usual, but there's no showstoppers, and everything is just looking for that first project to really do it. Coming back to promotion itself, there's 6 key objectives for promotion, and 3 of them are related to technology. So just very briefly, the first one was to establish interoperability between different technologies and concepts by providing specific technical and operational requirements, behavioral patterns, and standardization methods for different technologies. I think across the work packages that you've seen presenting today, we can call that one done. The second one was to develop interoperable, reliable, and cost-effective technology of protection for meshed HVDC offshore grids and the new type of offshore converter for wind power integration. Again, I think across the work packages you've seen today, we can call that one done. And lastly, to demonstrate different cost-effective key technologies for meshed HVDC offshore grids and to increase their technology readiness level by investigating and overcoming early adapter issues and pitfalls. And as you've just seen, for each of the key technologies here, we've taken big strides forward in that TRL. So again, the third objective, technical one for promotion, I think we can safely call done. Now, as we've mentioned earlier, we still need to cooperate to make sure that we get these different things lined up for interoperability and moving forward into the standards, but we've got a good basis and that work is already ongoing. So just a final thank you for coming, and we look forward to the first inaugural HVDC grid when it becomes. So just moving forward, to say that this was breakout session 2 of 4 on the build up to the final conference. So later this afternoon, there's another Q&A looking more at the legal and regulatory, and then next Friday, there's session 4 on the offshore grid planning, looking more at the roadmap to the end. And our final conference, if you'd like to join us then, is on Monday, 21st of September, and the sign up for that is still open. So a final thank you and farewell, and we hope to see you at the other events.